The broadcast is now starting. All attendees are in listen-only mode.
Hello. Good morning. I appreciate everyone joining us here on the webinar series. This is Paul Garrison. I'm the Sales Director here at Nimbix. Wanted to thank you all for joining us for the Compute30 HPC On Demand 101 webinar. As we promised to keep our presentations under 20 minutes to give you plenty of time to ask questions without going over our 30-minute limit we set on the webinar series. We will be answering the questions at the end of the presentation, but feel free to type them into the GoToWebinar panel off to your right, and we will answer them in the order they come in. Without further ado, I'd like to turn the presentation over to today's presenter, Nimbix's CTO, Leo Ryder. Leo?
Thank you very much, Paul, and thank you to everyone who could attend today. We look forward to giving you a great presentation and answering all your questions. If for any reason we run out of time and we can't answer all your questions on the live webinar, we will take your questions offline and make sure that they all get answered, by email. So without further ado, let's get started. We're seeing a rapidly emerging problem that's getting more and more critical as time goes on. Whether for scientific or business purposes, organizations have been and continue to collect massive amounts of data. This data is useless without big compute to make sense of it. The problem with big compute is that it's not efficient on commodity systems that many organizations already have. This leads to an insatiable demand for computing time on very high-end resources in order to get results in a timely fashion. Failure to get results in a timely fashion can lead to missed opportunities for business and society as a whole, depending on what problems we are trying to solve. The demand for compute time is so great that it's far outpacing capacity. Even if you already own some high-performance computing resources, chances are they're not enough to solve today's problems effectively. Current industry trends suggest HPC capacity growth is being outpaced by demand almost exponentially. Even if you are meeting today's requirements, it's unlikely that you can continue to grow your systems fast enough to keep up with what's just around the corner. It really is time to start thinking about new ways to expand your capabilities. Unfortunately, the industry as a whole is simply not equipped for big compute. Once you've run out of HPC resources, what spare capacity is readily available in-house is on traditional IT systems. These systems were intended for very different purposes than high-performance computing. While great for collaboration, productivity, and web services, these resources are simply not efficient for big compute. Large-scale computation is needed to make sense out of the massive amounts of data we need to process. This mismatch of existing resources and requirements has industries looking at all possible options when it comes to solving this problem. Before we go any further, let's review the basic requirements for high-performance computing. Bare metal performance to get the most out of our systems and avoid costly overhead. High core count and large amounts of memory to achieve the type of density we need to solve big compute problems. Accelerators and coprocessors to give us the extra boost we need to get the job done faster. High speed, low latency interconnects to avoid bottlenecks in our parallel processing. And of course, a workflow-centric architecture that's optimized for batch processing so that we can actually run the HPC applications that we need. HPC on demand is poised to change the way we think of solving the need for capacity to keep up with our workloads. Traditionally, if we wanted more capacity, we had to build it. This requires high-performance computing hardware and software, as commodity systems just won't get the job done. We also need people with hard-to-find skills in building and operating HPC clusters and applications. And let's not forget that high-performance computing draws more power and produces more heat than ordinary computing, requiring specialized data centers equipped to keep up. The result of building the capacity in-house is a very complex and expensive proposition. It's an investment that can take years or even decades to pay dividends. If instead we run our HPC capacity as a service on demand, we can get started with zero upfront costs. We pay only for what we use when we use it. And we enjoy elastic scalability from a public cloud that's growing as fast as we can consume it. In short, running HPC as a service on demand can help us solve big problems right now. But there's a catch. The most popular form of public cloud compute capacity is in the form of infrastructure as a service. This is the least common denominator in cloud computing. It's actually a technology that was born out of spare e-commerce capacity years ago. It was simply never intended for high-scale computation as it's slow and oversubscribed. The biggest public cloud infrastructure as a service offering actually has the term web services in its name, making it very clear what it was in fact intended for. Infrastructure as a service can be the worst of both worlds because its do-it-yourself nature is almost as complex as building your own HPC, but it can cost more in the long run since you need larger scale to realize acceptable performance. It really is no wonder that our friend is pulling his hair out, as he struggles to bid for sluggish instances just so he can start loading his software on them and configuring them to communicate over slow links. All he wants is a quick way to process his data, not a virtual jigsaw puzzle of processes and tools intended for other purposes. Luckily for our friend and for the rest of us, there is a better way. It's called software as a service. Software as a service puts the focus back on applications and workflows, giving you great time to value. Service providers deliver the applications you are already familiar with and handle orchestrating all the HPC resources needed to run them efficiently for you. All you need to do is choose your application and scale, provide your data, and wait for the results. There is no complex installation to worry about, no instances to log into, and no configuration hassles to deal with. Some software as a service providers leverage real HPC infrastructure, meaning much better performance and lower overall cost since your jobs run faster than on comparable infrastructure as a service configurations. In this model, you pay for results, not just compute time. Software as a service is the easy-to-use, purpose-built HPC alternative to infrastructure as a service. With this paradigm, the promise of HPC on demand is finally within reach. Unfortunately, there is always a catch. In this case, there's two. First, what happens if the application you need is not in the service provider's catalog? Second, what if you already have a workflow and you want to integrate with HPC on demand seamlessly? Software as a service starts to fail on the promise of HPC on demand when the service provider does not offer the application or applications you need. Your use case requires that you modify and customize the application or applications to get the job done. You already have your own custom application and you have to use it. You already have a larger workflow and you have to integrate with one or more HPC applications on demand. Or you simply need more automation, more flexibility, and/or more diverse hardware platforms in order to solve your problems quickly and efficiently. Finally, we have the solution to deliver high-performance computing on demand. It's called Platform as a Service. Platform as a Service extends HPC on demand with more flexibility on one end and more interactivity on the other, effectively bridging the gap between infrastructure and desktop applications. Platform as a Service unifies these broad capabilities into one large workflow, so you don't need to move data back and forth to get different steps of work done. We call this workflow Build, Compute, Visualize, all on demand. Our Jarvis platform covers the full spectrum of application workflow and lifecycle management, whether you're using existing applications and processes or you're building your own. In this example, we'll observe Build, Compute, Visualize at work for a CAE simulation. First, we would bring our data set to the cloud. Next, we would pre-process our model using the interactive module of our application. Then, we would run the parallel simulation at scale using the batch module of our application. We would view the results of the simulation again using the interactive module of our application. When we're finished, we would end the workflow and download the results from the cloud. In this next example, we'll observe Build, Compute, Visualize at work for a custom application. First, we would implement or modify our source code or application configuration. Once finished, we would snapshot our application environment. At this point, we're ready to bring our data to the cloud for processing. Next, we would run the parallel computation at scale using the batch processing module of our application. Then, we would render the results of the computation in a graphical workspace using the visualization module of our application. When we're finished, we would end the workflow and download the results from the cloud. At any point in the future, we could return and either run our application as is or make further modifications before the next workflow. In next month's episode of the Compute30 Technology Series, we'll take a closer look at Build, Compute, Visualize concept, including the powerful API and interactive portal capabilities that make it possible. In summary, every solution starts with a problem. Science and industry is collecting massive amounts of data that needs to be processed. As a result, the demand for big compute is far outpacing capacity. Much of the capacity that is readily available is simply not suitable for high-performance computing. There are a few alternatives that we've considered. First, we can always build more capacity, but this is expensive and complicated, so we're looking more and more to the public cloud for help. Unfortunately, a large part of the public cloud is in the form of infrastructure as a service, which is not suitable for HPC. HPC-focused software as a service has promise, but falls down when applications are not available or when workflows are complex. The solution to the HPC on-demand problem arrives in the form of platform as a service. The Build, Compute, Visualize paradigm expands the capabilities of the platform for added flexibility on one end of the spectrum and interactivity on the other. This workflow excels at traditional HPC applications such as CAE, and it also enables developers to build or customize their own applications to later run at massive scale. In short, HPC on demand is simply about solving big problems quickly, efficiently, and cost effectively. Thank you very much. Back to you, Paul.
Thank you, Leo. Just while we give everyone a second, we're going to go ahead and have the Q&A session, or portion of the webinar now. If you have a question, please enter it into the GoToWebinar panel that should be off to your right. And while we're letting everyone put in their questions, I'd like to take a moment to invite everyone to attend our other Compute30 webinar series. We're actually broken it up into two tracks. There's the technology track, which, as Leo mentioned, next month on the 18th, we're going to dive a little bit deeper into the build, compute, visualize methodology of Jarvis. And then we also are doing an industry track where we're going to actually break down into more case examples of how HPC on demand can be used in different industries. Again, that you can find information on this at nimbix.net/compute30. With that, I'd like to go ahead and start the questions. Leo, we've got our first one here is, how secure is this?
Sure. The short answer, of course, is it's very secure, but I'll embellish on that a little bit. So there's three layers to our security that are important to understand. So first is the physical facility security, which means that our data centers are SSEA 16 SOC 2 certified. There's 24/7/365 personnel. There's a dual authentication mechanism, so you have both a key card as well as biometrics. So once you get into the building with your key card, to actually get into the bunker effectively inside of the data center building where our computers are, servers are, you have to do a biometric scan. So it's very, very difficult to even get inside where our systems are. Obviously, it's open to authorized personnel only, Nimbix employees only, and certain Nimbix employees only. So that's number one. Number two, we practice workload isolation. So we mentioned already that a very key requirement to HPC is bare metal performance, which means that we're not virtualizing workloads, which in extent can also mean that some people put multiple virtual machines on one host. We don't do any of that stuff. Each system runs its own workload at a time, so that you'll never have two tenants or two customers running code at the same time on the same physical computer node. That's isolated to just that job that's running for the length of the job. So what this means is that there's no risk of any cross-contamination of memory or processing. Since we don't actually use a hypervisor, there's no risk of rootkit type attacks that are designed to get underneath hypervisors and wreak havoc that way. So really, the code is just not there to interfere with, because it's only your code running on that particular node or nodes at that moment. The third way, of course, is every single transfer, both in and out of our data center, as well as between our computer nodes, even inside the data center, is fully encrypted using strong encryption. So we don't do any unencrypted data transfer, data movement at all. So that keeps, anytime that data has to move in and out or between nodes, it's fully encrypted and secured.
Thank you, Leo. Next question is, what is your network topology? If n nodes are used, how will they be connected?
Sure. So basically we have two elements to our topology. One is there's obviously a high-speed Ethernet topology, which is switched, and it's actually this allows the nodes to communicate either with each other or in and out of the internet, or allows you, depending on the type of resources you're consuming, if you're consuming a Nimbix application environment to build your own application, then you would be able to log into the node. If you were using a 3D workspace environment, you would be able to connect to it with a 3D viewer. So that all flows over, of course, Ethernet, because it has to talk TCP and so forth. But the other element, which is also very, very key to HPC, is that most of our nodes, certainly all of the nodes that are involved in parallel processing, are connected with InfiniBand. So your application is actually free to use RDMA, which is the preferred InfiniBand mechanism for HPC because it has the lowest overhead and it's very, very fast. And that's a separate network topology from the Ethernet one that's used to communicate over standard protocols. So if you have applications that pass messages between different nodes in parallel mode, then you can leverage InfiniBand to do that and achieve, in some cases, hundreds of times performance that you would with Ethernet.
Okay. Thank you, Leo. Next question is, what comments can you offer regarding the transfer of large amounts of data as a bottleneck for these kinds of large analysis?
Right. Obviously that's just an issue with cloud, and particularly cloud for processing large amounts of data such as analytics and so forth. But there are a number of ways that we mitigate that. First, you have to do less data transfer because you can actually, the fact that you can do the full spectrum workflow where you can actually build your data or capture it if you're doing a big data workflow, for example, you could actually capture it from our cloud. So without having to first capture it offline and then upload it, because we have the ability to have a multi-step workflow. So whether it's big data or maybe you're designing a model or you're designing animation or whatever it might be that would then move on to computation, you can do that directly on the cloud, either interactively or in the case of data capture, you can simply leave a job running that captures data. Then you would compute it, and of course there is no movement back and forth. One thing that we don't do is our computation and our data storage are part of the same service. So we don't have to move data from object storage from our own object storage into our computation like some other providers do, because they're literally, it's just part of the same fabric. So once it's in our system, there's no movement to actually process the data, pre-process, process, post-process. That can all be done without moving any data. And then, we do have situations where customers have such a massive amount of data that they need to actually host it, close to our compute. And we do offer, some managed services that would allow you to bring your own data storage systems into our data center. And in fact, we have some arrangements with some customers to do that. But typically, most customers doing HPC on demand today are working with data sets that are manageable. And again, the fact that we support all elements of the workflow means that you don't have to move it back and forth just to move from pre-processing to processing, which is a big advantage.
Thank you, Leo. Next question is, how do software providers optimize their applications for Nimbix's high-performance hardware? Are proprietary development tools available under license for remote use?
Sure. Absolutely. It's an excellent question. The most popular, so today, the most popular form of high-performance, co-processors and accelerators are general-purpose GPUs used for both computation as well as rendering. So on the computation side, we support CUDA, we support OpenCL. These are all NVIDIA type systems. So our platform, when you develop on our platform and you select one of our resources to write your code on and to test it, you can select a resource that already has both access to the hardware as well as the development tools loaded on it. So you don't have to worry about, okay, now I got this, environment, and okay, let me go download the, the CUDA toolkit and the NVIDIA drivers and all that. No, that's actually all pre-configured. So you really just get to work. You don't have to worry about configuring the infrastructure. We take care of all of that. We also have other accelerators. Xeon Phi would be kind of the next most popular one. So right now, what we do provide is the ability to program the coprocessor using the sort of the free tools that Intel offers to control and download code to the coprocessor. We are looking at ways to support developer type licenses of the Intel compilers and things like that, but right now at the moment it is a bring your own license if you wanted to use an Intel compiler instead of what's available freely. But what we don't make you do is figure out how to install the driver and all those complicated things that are involved with a many-core processor.
Thank you, Leo. Looks like we've got about 5 minutes left, so probably time for 1 or 2 more questions. Again, if we don't get to answer your question, we will follow up one-on-one with you to help answer these after the webinar. The next question is, why is bare metal such an important requirement?
Sure. Basically, you know, it's kind of it's 2 schools of thought, right? One is that with efficient virtualization, we can get close enough to bare metal performance that we don't have to worry about, you know, giving people direct access to the hardware and so forth. Obviously, we subscribe to the school of thought that if you're doing high-performance computing, you want to eliminate all possible overhead. In fact, it's not uncommon, especially if there's any developers on this call, that you've spent sleepless nights, you know, just eking out that last 1 or 2% of performance out of your application. So it'd be really sort of, you know, self-defeating if you then went and put it on a hypervisor. That would rob you of some baseline level of performance just for the fact that it has overhead to do the processing. So there's a kind of a general term called hypervisor tax that really, you know, it's kind of a marketing term, but it really refers to the overhead that hypervisors bring. And hypervisors bring overhead in 2 different ways, and then there's a third way that's really more of an implementation detail for the service provider, and we'll get to that. But the 2 ways are, one is you have just the fact that you have this you know, piece of code that's managing the system before your code can actually run, or actually before the kernel that your code runs on can run. It's an extra layer of processing on the system. No matter how efficient you make it, you still have to go through that code to do many, many things. And that, of course, robs, you know, baseline performance. The second thing is that hypervisors generally abstract most of the hardware away from the system. So there are some cases where some virtualization vendors and service providers are supporting pass-through of very specific devices. Generally, those devices are either not very powerful or are kind of specifically designed for virtualization. So they're designed for oversubscription, which we'll get to in a minute. But needless to say, not all devices support this type of thing. For example, if you wanted to use a Xeon Phi, it would be very difficult to do that in a hypervisor environment. So what, you know, hypervisor designers and vendors and service providers resort to is emulation of hardware. In some cases, they use paravirtualization to speed things up. But again, you're just adding layers and layers of complexity, and every layer that you add slows down your processing. So you could easily lose, you know, even if you only ran one virtual machine on that node to do some high-performance computation, you could easily lose 5, 10, 15%. We've seen benchmarks actually published by hypervisor people where something as simple as compressing a file runs 20% slower inside a hypervisor environment. So obviously your results will vary, but that's a reality. That's called the hypervisor tax. The next thing that's really more of a way that the service provider decides to implement the hypervisor, you have to remember that virtualization, the purpose, the reason that it started to be used, it was to reclaim wasted capacity off of servers. So what was happening is people were running applications on servers and they weren't getting full utilization, especially if they were web services or application services, because these applications tend to wait for input. So there's a lot of time when they're idle. So by putting more and more work and oversubscribing that hardware with more and more virtual machines, they could kind of balance that out and get back to a 70-80% of utilization. Well, as high-performance computing people, we know we have no problem putting 100% utilization pressure on any given hardware, the way that our code is written and the purpose of our code. So the fact that, you know, when you look at web service vendors or you know, commodity cloud vendors that have designed their entire infrastructure and their business model for oversubscription, for running more than one workload on a server at the same time, well, what happens is if you end up on a server that's running 2 workloads, your workload will run at least half as fast. So that's kind of a non-starter in an HPC workload.
Perfect. Thank you, Leo. And I think we're just about at the top of the hour. So again, want to take a chance to thank you for your time, Leo, and thank everyone for joining us here on the webinar. We will have a recorded copy of this session posted to the Compute30 page on the Nimbix site probably by tomorrow. If for those of you all that we didn't get to answer your questions today, we will follow up on a one-on-one basis after the webinar and help get you those answers. I do encourage you all to please go out, take a look at the other tracks and webinars that are coming up. Our next one again is on the 4th of next month, and then the next following technology one that Leo mentioned is going to be on the 18th. Again, thank you for your time, and look forward to seeing you at the next one.
Thanks, Paul, and thanks everyone for attending. Goodbye.